essentially I treated this whole thing as one lecture, these two blocks. So we're continuing with lecture 1. And as I just said, so we basically, before the break, we basically did this intro now. And I wanted to now, first of all, tell you about multiscale finite elements. But before I do so, there is one thing I wanted to, oops, I switched to something else. One thing I wanted to talk about quickly, and that's the question that came up at the end as well. So what sort of coefficients, why is the coefficient not in W in 1 infinity? So let me do this splitting again because that worked quite well. So what situations do we have? So especially in UQ, and I know that many of you are working in uncertainty quantification, then typically A is some random field, and then this is typically not in W1 infinity, or can be not in W1 infinity, especially if you're doing a Bayesian inference. You don't want to put smoothness into your problem when you don't know it has smoothness. But a more simple situation that you could come up with is that you might have some piecewise constant coefficients where, say here, you've got one value, beta, and here you've got the value alpha in the language of what we had before. Then globally, you know that the solution is no better than, in general, globally the solution is no better than u in h1 plus gamma for gamma less than a half. And locally, you can exploit, so you can exploit local regularity in our interpolation result that I had earlier. But even locally, so if I draw, for example, the following situation, so you could have a situation where the coefficient is beta in here and alpha in here, and now you let beta over alpha go to infinity, so the contrast in the two media goes like to infinity. Then essentially, if you live in the alpha region, in omega alpha, then this behaves like a Dirichlet boundary condition. So the region where the coefficient is essentially high versus the one where you're in, if this is water, I always think of it as water. If water flows and you have something that's essentially super permeable here, then the water just disappears, which means the pressure goes to 0. And so essentially this behaves like a Dirichlet boundary condition, whereas in the beta region, in omega beta, the boundary behaves like a Neumann boundary. And so, again, I don't know how many people have done classical finite elements, but this is the classical L-shaped domain here, and even though I drew it not as an L, and this has only h5/3 regularity in omega alpha. So even locally, the solution is not H2 at the reentrant corner. And I can even come up with an even worse situation. And this is the so-called Kellogg function. So if I, again, in the same pictorial language that I've used so far, beta in these two squares and alpha in those two squares, then we have a cross point. And And again, if you think about flowing water, you've got very fast flow in these regions and almost blockage in these regions. So you essentially have to squeeze everything through the eye of a needle. You've got to get everything to go through this point if there is some pressure gradient. And so, in fact, you can even work it out analytically that this thing is H1 plus alpha, where we can write down the alpha. Alpha is 2 over pi arctan of 2 times square root beta of alpha. Sorry, I don't want to bore you, but this is going to be important for the next story I'm going to tell you. So basically, if alpha is much smaller than beta, this is approximately 4 over pi square root of alpha over beta. So let's assume, like in a subsurface flow situation, you can really have rock types that have 1,000,000 times higher coefficient than the others. So if this was 1 over 1,000,000, then this is square root is 1 over 1,000. So we're talking about that the solution is H1 plus H1.001, H1 plus 0.1. Yeah? So it's really, really not regular. Okay, so why am I specifically telling you this? Just to show you that the old school, what in the oil industry people used to do in the 90s, they basically took their domain, they put a coarse mesh on, and then for each block, they just solved the cell problem. So they basically took this block here, and the coefficient might do whatever it does in there, and they essentially said, okay, if I put pressure 1 here and 0 here, and put the no flow boundary condition here, then I can solve a cell problem to compute essentially the homogenized coefficient AT hom, a constant, on this element. I'm using squares from now on because it's easier to work with than triangles. So AT hom would simply be the average of the flux through this region. So you press water through, or you have a pressure gradient through this region, you can compute the solution of this cell problem, and you end up getting that the solution to this cell problem integrated, or A times grad phi of this cell problem, which is the flux, averaged gives you a homogenized coefficient. But now think of the following scenarios. What's the issue? Let's assume the true coefficient on this T looks like this. Well, we've got four triangles here, or 4 squares here, and the coefficient looks like this, say. Yeah? Then obviously once I homogenize, this will be roughly looking like a cross point. And if I have this situation, this will also be roughly looking like this thing here. So whether I have a region where this high probability region is completely decoupled from the neighbor and it needs to go through the middle here where the coefficient is alpha, or I have a situation where it just goes through a narrow channel, behaves exactly the same, and I've created an artificial cross point where my solution has the regularity over there and where my finite element doesn't converge. So this is an issue. So just purely upscaling and then working with classical tools as they used to do, then they use classical finite volumes to discretize this, is going to create these artificial cross points which have problems. And the other thing I wanted to say before going to talk about, no, I'm going to skip this last bit because it was something about the heterogeneous multiscale method. I'm just going to skip that because of the time. So the crucial point now that I want to make is, rather than using this upscaling, we're going to work again, like my mantra from the beginning, on the function space. So we're not going to manipulate the coefficients, we're not manipulating the ansatz space, the VH. Technology works. Wow. Good. So we're gonna now, I'm gonna now describe to you the first of these methods that was developed, where instead of doing this upscaling, people came up with the idea we just change the ansatz space, and they were coined under the name Multiscale Finite Element Methods. So this is the first paper by Tom Howe and Xiaohui Wu. They essentially had the following idea. So we want to work on a scale capital H. So all the meshes I've drawn at the moment, from now on, I'm going to use capital H to identify them as the coarse scale, at the scale at which we want to simulate the macro scale. And then I'll have a little h which I'll describe in a minute. So the coarse mesh is our mesh, but instead of using polynomials on the coarse mesh, so classical finite elements in my 101 in the earlier lecture, I would use quadratics, cubics, linears on each element. Instead, we're going to formulate a cell problem as such. For each vertex, so let's call this vertex here xj in the middle, we're going to compute a phi j ms on a finer scale finite element space. In the analysis later on, I'm even going to solve this in H1. I'm just going to work out the function that solves this PDE, but in practice, obviously, you work on a finer grid. So you can see here, for example, whatever that is, 16 or 10 elements across. On this little, on this finer mesh, I'm going to solve a problem, namely the homogeneous PDE, but with the correct PDE coefficient A. And I'm going to use as test functions also my finite elements, classical finite elements here, and as boundary condition, I choose some boundary conditions on the red edges here. And this is where sort of the cooking recipe comes in, because obviously if I knew what the boundary conditions were, then I would have solved the problem. So I need to artificially set some boundary conditions. And the simplest way to do this, so what do I want of these boundary conditions? They should obviously be conforming, so whatever boundary condition I choose for this edge for the function on the left should be the same boundary condition I choose for the function on the right, because I'm going to have to build a function on the other element as well. I'm going to fix a function on the edge such that it's 1 at one vertex of the edge and 0 at the other. All this can be done for 3D, 4D, 5D as well, but I'm going to just describe it in 2D. So I'm going to fix a function that's 1 here and 0 here. And for this edge, I'll do the same. 1 here, 0 here. And for this edge, I'm going to put 0 all along because I want this function to be like finite elements, to be 1 at that vertex and 0 at all other vertices. And if I do that, and I have one function that's 1 here and function that's 0 there, and vice versa, then the two of them should add up to 1. So they should form a partition of unity on the edge. So one way to do this would be linear. So I just make this function 1 and then linear to 0 here, and this function down here I make 1 linear to 0 here. Okay? So that would be the simplest, and that's the one we use for our analysis later. Or, if there is some coefficient variation along this edge, if A varies along this edge, you could solve a 1D problem. You could solve a 1D PDE problem, 1D ODE problem, where you solve the same problem but 1 dimension lower. And this is how you can already see also how you would do it in 3D. You first solve along an edge, then you solve along a surface, and then you solve in the interior of a tetrahedron. But no matter what you do is you essentially set a fixed boundary condition, and then you solve this homogeneous PDE problem locally. As we come up later, is if you oversample, if you actually solve on the slightly bigger domain and set the boundary conditions out there, that's actually going to help us to overcome scale separation issues. If the coefficient actually happens in one triangle to be constant, then this construction is nice because it just brings back the linear. So if the coefficient is anyway constant, then this problem actually reduces to nothing, and I get my piecewise linear function back. So this can also be done in an adaptive nature. In regions where the coefficient does something fancy, compute. In other regions, just take your piecewise linear. So this is what a function would look like. So you see here where the darker regions are is where the coefficient is large, and what we will see in a minute, it's the energy, the energy norm of the function that matters. And in regions where the coefficient is large, they get multiplied with a very large number in the energy norm. So you would like the gradient of the function to be as small as possible. In regions where the coefficient is small, the gradient can be larger. So you essentially would like to construct functions that are flat in regions of high permeability and have their gradient everywhere where the coefficient is low. So this would be what this function would look like. So what are other properties? So they do, like standard finite elements, form a partition of unity. So standard piecewise linears form a partition of unity, that is, at any point in the domain, if I sum up all the basis functions, I get 1 back. So they can represent constants, which is really important in solving PDEs, because the constants in solving this PDE are Laplace, because the constant is the kernel function of the PDE. They are aharmonic on each t. So this you can also call aharmonicity. This means they're satisfying the homogeneous PDE locally. So they're aharmonic on each t, and they actually, by making the boundary conditions as such, they are conforming. So they're basically still continuous, and therefore they are actually a subspace of V. And so we can use our Galerkin projection, we can use all the tools, we can use Sear's lemma, we can use all the tools I described to you. So what we're going to do is, instead of choosing the piecewise linears as our basis, we just take these phi j ms as our basis, and then we cook as before. We just compute the stiffness matrix as before, just with the new basis functions. We get a matrix as before, just with the stiffness matrix that's got these entries, and I represent my true solution then, or reconstruct it as a linear combination of these basis functions. If you actually genuinely want to then use information at a particular point, you need to go back to the fine mesh, because these functions live on the fine mesh. But if you're only interested in macro quantities, macro scale quantities like averages, then you don't. You might be happy with the coefficients of your problem. So is this clear? So the crucial thing is, I really am not doing very big rocket science here. I am solving small problems locally with the boundary conditions being based on the basis I gave you on the board before. but they locally now solve for the coefficient, so they might do a bit of fancy stuff and not just linear. And then I put them together in the same way as we did on the board for classical finite elements to form our method, to form our matrix system, and to solve. So why is this going to give us a better error estimate is now the question. And to do this, we're going to focus on 2D, and we're going to focus on the case of a periodic function. Okay? So you really have to think of this. This could be or maybe I do it in 1D, because in 2D it's going to be a bit hard. So this could be that the function basically is just some sine function and varies across, but it could also be that I have a certain cell problem, y, and on this cell problem the coefficient is high in the middle and low on the outside. And then it's periodic, so this coefficient is just repeated across the whole domain. High, low, high, low, high, low, with the same frequency. Now the local problems are solved exactly, so I'm not using a finite element mesh, so I'm solving my multiscale basis functions in H1 on T. And as a boundary condition I use my classic finite elements piecewise linears. Okay? So the local aharmonicity is basically that integral over T A grad phi JMS grad phi for all phi in H01 with this boundary condition is 0. Then we have the following result, which was proved in this follow-up paper by Hao and Wu together with Tsai. If the exact solution is H2, so this would be this setting here. If the solution oscillates, if the coefficient oscillates, but is H2. And the homogenized solution, which I write down in a minute, is also H2, but also W1 infinity. So one less derivative, but higher, but pointwise, or essential soup. Then the multiscale finite element solution as computed on the previous slide satisfies the following error bound in the, this is my V norm from before, no, this is the full H1 norm. It's bounded by a constant times mesh size over epsilon times f if the mesh size is smaller than my period of my periodic function. And it's bounded by a constant times h plus epsilon f plus this term here if we are not resolving. So the interesting thing is obviously the second part where essentially the period is so fast that on one triangle, so this is h, where on one triangle the function does many, many oscillations. And you see immediately this is a little bit nasty here, and we can get rid of that in our later methods, because this is what's called a resonance error. So when you get close to being h equals epsilon, then this thing actually doesn't disappear. And so you're in a little bit of trouble in the region where h is roughly equal to epsilon. So you really want, and this is now what I always call scale separation, you really want to be in the setting where epsilon is significantly smaller than h for these methods that require scale separation to work. Otherwise this thing will not go to 0. Okay, so I think that's it, yeah. So let me switch to the board again. I want to prove this result now. In the periodic setting. So first of all, just one comment on the first statement, where h is less than epsilon. Basically, we use that the H2 norm, which we assume that exists, actually is less than or equal to a constant times 1 on epsilon f in L2. So you essentially see the period, but period in this case is quite large. But you see that the curvature of the solution depends obviously on the second derivative, which is like the curvature depends on the scale, epsilon. Because this is integrals over the whole of omega. So on the whole of omega, you could still have many oscillations. And then it's classic, and then classical theory. By the way, this whole thing is, I have it on the slide later on. This is basically from the book, Effendi and Hal, 2009, chapter 6. So here is the book, if you're interested. But it's actually in the in this 1999 paper by Hal, Wu, and Su. So now let's look at the case where h is bigger than epsilon. And here I already had on the statement, I said there is a homogenized solution. So I need to first tell you a little bit about homogenization theory. So I'm gonna be very schizophrenic because of the literature. I'm gonna mix English and American spelling all the time. I still don't know which one to use now that I'm in Germany, but so anyway, I'm trying. Normally I was brought up to use S's everywhere, but then all the literatures has Z's, so we'll see. Okay, so here is the homogenized equation. So let's call the differential operator L. L0 U0 is basically minus divergence A star grad U0 equals F in omega. So this is our homogenized equation. We still have our Dirichlet boundary conditions on partial omega, and the A star, the homogenized coefficient, is a constant, but it's a it's a matrix valued constant because we will get, when we homogenize, we will get different effects from the 1, so the XX, YY, XY, and YX components, as you'll see in a minute. I didn't remind you. So A, remember, so this is not here anymore because I don't have the slides here. So remember A was, oh, I can put it up there. So A was Y periodic, yeah? And Y was just a unit square. So over this unit square, so obviously I could leave this 1 over Y out because that's just 1. Integral Y. Now I need to go over the dimensions. AI and JX. Delta LJ plus D chi J dxj tyl, sorry, dy. Okay, so there is still more objects that I haven't defined yet. So now we're going to have to define the chi j. So chi j is a function of y. It's the periodic solution, so periodic boundary conditions, of the cell problem well, I write it down so that you have the word ones down. Cell problem. Minus gradient now with respect to y. A of y. Now we are on the period cell. We are on the 0, 1 squared. So on a micro scale in some sense, once epsilon gets smaller. So one other thing. I prepared this obviously with both my slides and the board ready. So remember the PDE we're solving is A of x divided by epsilon grad u equals f. So here we are essentially making the coefficient oscillate faster and faster and faster if we reduce epsilon. But for the cell problem, we're just going to look at one of the period cells, 0, 1. Equals, and now here we need the derivatives of the function. This is why we need the function to be smooth enough. A j by dx dy j. So on the right hand side, we put the derivatives in the ith component. This can't be right. It should be I, because this is obviously chi j. Yeah. Okay, so these a's are typically symmetric anyway, so it doesn't matter whether I get ai j or aji. Okay, I need to double check this, whether I copied this wrong. And this has no boundary conditions, it's periodic, so you need to specify, or it has periodic boundary conditions, so you need to specify an extra condition, and namely the extra condition is that we want the average of it to be 0. Okay, so does that, is that clear? So we have, this is essentially what there will be a whole lecture again to give you homogenisation theory, but essentially what the bottom line for this elliptic problem is that if you compute the coefficient A star as such with these cell problems, then I can solve this homogeneous PDE now. So remember, this is now constant. This is now constant, so it can actually be pulled out. Apart from the fact that it's a matrix, so I can't really pull it out, but it doesn't have any derivatives, or it doesn't appear anymore, yeah?
The x argument of the aij, where does that occur?
Just the y.
Is it y? Yeah. Oh.
Sorry, yeah.
Mm-hmm.
Yeah. Okay. So now I want to use obviously this u naught, or I want to tell you that this u naught is good. I mean, it's a good approximation to u when epsilon goes to 0. That's the whole point of homogenization theory. And for smooth periodic settings, that actually is a fact. So you can just solve the homogenized equation, you get a good answer. Now, we have a omega. I'll assume omega is convex. So I assume that omega is a square, for example, or something convex. Then we know that u naught is in H2. So the homogenized equation is just a Poisson equation in some sense. So it has an H2 solution. And we now write down the corrector, or rather we write down the derivative special function u1, which is built from these cell solutions, which we now evaluate at x over epsilon times the derivative of the homogenized solution evaluated at the macro scale. So if I take the derivative of this smooth function, h2 function u0, multiply with the cell function times x over epsilon, that function I'll call u1. And now I'm going to calculate the first order corrector. And this first order corrector, can you see this from the back as well? I was told that before I didn't push it far enough up.
Yeah, all good.
So this satisfies the original equation. So minus divergence A of x over epsilon grad theta epsilon, 0 also in omega. So this is just for the theory, you don't compute this normally. But if you were to use homogenization theory and you want to get your convergence results, you do need to compute this as well. With minus u1 of x on the boundary. So when you compute this u1 of x, you may actually get boundary effects on the global boundary that you need to correct for. Something near the global boundary at partial omega can pop up in these derivatives here, and you need to calculate a corrector here. And what's the result now? So the lemma, there is many of such results, but this is a result by Moskov and Fogelius from 1997. Is that there exists a constant independent of u0 epsilon over the shape of omega, such that u minus u0 minus, and now we get the first order corrector, epsilon times bracket u1 plus theta epsilon h1 of omega is less than or equal to a constant times epsilon times u0 h2 omega plus f L2 omega. Just double check this because I'm just a little bit worried now. But now we know that u0 is h2 and we've already done this. This is actually bounded by constant times the right hand side. That was our Lax-Milgram result. No, this was not Lax-Milgram, that's a regularity result. Okay. So in essence, we get that the regularization error, the error by taking the regularized solution, adding the first order corrector, is of order epsilon. So if epsilon goes to 0, I can safely solve this homogenized problem. Okay, now comes we're actually proving that the multiscale finite element method, which doesn't need to compute all these projectors and correctors and everything, that it also, the error goes down with epsilon. And here is the really cool observation. By computing these local cell problems, we can do homogenization also on the cell level. We can do homogenization on the element T. So we look at the multiscale finite element interpolant of U0. So I wrote down the piecewise linear interpolant before on the board. So let me now write down the multiscale finite element interpolant. I call it from now on Ui of x. And the interpolation operator I call IHMS. But I'm not interpolating U, I'm interpolating U0, the solution of the homogenized equation. And that's simply sum j equals 1 to n over all grid points, homogenized solution evaluated at the grid point, times multiscale basis function phi JMS evaluated at x. And this is obviously an element in VH multiscale, in the span of my basis functions, multiscale basis functions. And now on each element, in our closed mesh, we write down the whole shenanigans, all the homogenization work, what I did here for the global solution U, I'm now going to do for UI. So I'm going to write down the homogenized solution UI not down. So this UI not satisfies L naught UI not equals 0, but importantly we're solving this on a triangle. And with boundary conditions being given by the interpolant. And here we use the classical interpolant. So this is our boundary data, because that's what we used as our boundary data. Remember, we're using piecewise linear boundary data on the boundary of T. So I'm writing down the homogenized, all these things are just for the theory. I'm writing down the homogenized solution of the interpolant, multiscale interpolant on an element T, which by this we immediately see that UI naught, so the homogenized solution of this interpolant, is in fact the classical finite element interpolant of U naught on the boundary, in T. And then, in order to use Moscow-Fugelius, we also obviously need U1 and the theta epsilon again. So we need to unfortunately write all that down as well. So P UI1 is again sum j chi j x over epsilon dui0 by dxj of x. That's my UI1. And the theta epsilon theta I epsilon. That one we need to solve only on the triangle in H1t, like we did over there for in H1 omega. So here we have L epsilon theta I epsilon equals 0 in t, and theta I epsilon equals minus ui1 of x on the boundary of t. This is exactly mimicking what we did globally, and now we have what do we have? So we have a u0, we have a u1, we have a theta epsilon, we have a ui, and then a ui1 naught, ui1 and theta I epsilon. And now we put everything together. So first of all, I observed that Fogelius and Moskov holds also for this guy. So due to the lemma above, we have that ui minus ui naught minus epsilon times ui1 plus theta I epsilon h1 on t is less than or equal to a constant times epsilon f L2 on t. So we have this is less than or equal to a constant times epsilon f L2, and this is constant times epsilon f L2. I'll move it up now, so it's going to be easier. See if I can get away with these 2 pages, and I can keep the rest on the board. Okay, so now I want to put everything together. So one observation more here, maybe I put it still here because I have a little bit of room here, that the L epsilon ui, remember, is 0 on t. So it's a harmonic function. So ui is a harmonic function on t. So now we can write. Now we do the usual numerical analysis game. We're gonna add and subtract lots and lots of terms. Okay, in this case, really lots and lots of terms. Okay, I'm gonna write u minus ui. So u minus the equivalent, which is what I need to bound from above, as u minus u naught minus epsilon u1 plus theta epsilon. So I've added these 2 terms, so I subtract them again. So plus u naught plus epsilon u1 plus theta epsilon. Then I'm gonna put minus, I need more space. I wanted to make this nicer. Visible anyway. So u naught plus epsilon u1 plus theta epsilon. Then I subtract now the second part. So u I naught minus epsilon u I1 plus theta I epsilon. So I need to add that in again. So plus u I naught plus epsilon u I1 plus theta I epsilon. And then all I've left to put is this guy. I haven't put this guy yet. Minus ui. Okay, now let's inspect. So this guy is in the Bosco-Fugelius lemma. This guy is in the Bosco-Fugelius lemma for the interpolant on T. And then I have the middle terms. So basically, so thus using the homogenization results, for u on omega and for ui on t, we get that u minus ui h1 on omega. So the fact that I'm doing this on each element t doesn't matter, because once I integrate over all t's, I can just sum up the results. And I'm gonna get an f in the N2 norm in t there. And so if I take the square of that and sum it up, I'm just gonna get the f over all of omega. So the first two the red terms just give me c times epsilon f L2 t omega. Okay, that's the red terms. And then I have, okay, u minus ui naught, that's this term and this term, u minus ui naught, h1 omega, and I'm gonna take this term and this term, and I get epsilon times u naught minus ui naught, and then here I've got u1 minus ui1. And then I've only got the theta terms left, so I'm going to leave myself a little bit of space here. So here I get epsilon times theta epsilon in H1, and here I've got epsilon times theta I epsilon H1. Okay, so this essentially is classical finite element approximation theory, plus maybe a little bit. And this guy, including the epsilon, is less than or equal to a constant times h plus epsilon f in L2. And I've put this on the exercise sheet, which I'll give you in a minute. Okay? And then these guys are a little bit more involved, and I'm not gonna try and prove them or put them on the problem sheet. So this is going like square root of epsilon times u naught, the homogenized solution, in the W1 infinity norm on omega, plus a constant times epsilon times f L2. And then finally this guy here goes like constant times, this is the resonance effect term, epsilon over h to the half u naught in the W1 infinity norm. So both those you can find either in the Effendiev-Hau book or in the original paper. These are lemmas 6.7 and 6.8 there. Okay, so let's put everything together. So collecting all the bounds. And using Thier's lemma, we get, okay, so we know that the Galerkin solution that we're computing, so that would be multiscale H, is less than or equal to the infimum of all possible solutions in this multiscale space, so in particular less than or equal to the interpolant. So that would be u minus ui up to a constant here, and that would be essentially some constant times beta over alpha. So some constant times beta over alpha u minus ui h1 omega. And now I'm going to collect all the terms. So we're going to get constant times beta alpha, so this is now a different constant because I pick up lots of constants from over there. So this is just epsilon FL2, this is H FL2, this is H plus epsilon FL2, this is epsilon FL2. So there is lots of H plus epsilon FL2s here. So I get H plus epsilon F in the L2 norm. And then I get two terms where the W1 infinity norm props up, and epsilon over h square root is always bigger than square root epsilon because h goes to 0, so it's less than 1 typically. And so this term dominates this term, so we can absorb it into the constant, and we get epsilon over h to the half. U naught W1 infinity on omega. Close brackets. And that was what the result was that I had on the lecture, on the slides. Okay, breather. Okay, I think I have everything on the board. Any questions? Yeah?
I'm not exactly sure about the signs in the big expansion, but it doesn't really matter, though.
Yeah, it doesn't matter. And there was a few typos in the book as well, so it might be that I wrote one or two wrong as well. So in particular, I didn't double check fully whether this should be a minus here, and then at one point it was a minus and one was a plus, but this can all be cleared out there.
But in any case, it's not relevant when you do.
Yeah, because you're always upper bounding by some sum of some terms here. But I think the crucial thing to observe is we always in finite element analysis we add and subtract, for example, the interpolant in. But if you did it with classical finite elements, you just cannot use this result here, and you'll be dead with the classical, because locally on the element, the piecewise linears would just not approximate the solution well. So it oscillates, so the constant by which, so this construction here of the homogenized coefficient, you can see very clearly is not just averaging over the coefficient. This is quite an involved averaging procedure, which depends on the cell problem. And so you end up getting, essentially, when h goes to 0, when epsilon goes to 0, you just get the wrong answer. You had a question as well.
I have a question about the boring case. The h resolves to epsilon.
Yeah.
How do you mean this with the classical theory? So your ansatz space is still not the polynomial space, isn't it? So you use, of course, CS
No,
lambda.
it is. It is in that case. Well, it's almost. Because the function doesn't do much on an element, because h is... Yeah, okay.
It's not exactly polynomial, right?
Yeah, you need to a little bit. You need to interpolate first, and then you need to approximate the interpolation error. So you essentially add the normal interpolant in, but the interpolant, the classical piecewise linear interpolant, will be a good approximation at that scale.
Okay.
Yeah.
It's a bit more involved, but
Yeah.
not very.
Oh, I can put another exercise on there for Moritz.
Yeah. Another question. How would the proof change in the case that you don't use this boundary data prescribed by the head functions, but the more complicated one?
The oscillatory one, I haven't looked at it, I have to admit.
But does
So what I can tell you,
we exist in this case?
what I can tell you about, and that's actually the next slide I have as well, is in the context where you have piecewise constant and you have simple settings, Ivan and I did a result which we used for DD, and then Ivan wrote a paper with Tom Howe about it. When you have this setting, so say you have got some coefficient variation like that, where the inclusions are mainly islands, and smoothish, but they can overlap the region. They can overlap to the neighbors. Then doing the piecewise linear on the edge, and then extending harmonically to the interior, you can actually prove that that's even coefficient robust. So you can even get a coefficient robust theory for that. That depends not on the contrast.
And the piecewise constant, so it has to be adapted to the island which intersected, right? As you have drawn it there, yeah. Okay.
Yeah. So the basis function, as you can imagine, is basically along this edge it will look something like.
Yeah.
And then you do that on all three edges and you extend to the interior, which will be flat here as well. And then you get a basis function, and in that proof we did in that paper from 2007, we showed that that's robust. And then for DD, and then Ivan did a paper. I go to the. Is anybody else got a question on the board? Because then I go to the talk because I had this quote. Yeah.
I just wanted to ask a question about U1. Can you maybe give a quick reasoning about how do I know that I will need this on the boundary for the tetra?
No.
Because
So this is basically taking. So this essentially incorporates the local variation in a cell, and then scale to the right length, and you take the derivative of the homogeneous function with x. So this is in some sense the gradient of u. So it's the first order. So if you did a Taylor expansion, you would have u0 plus epsilon times delta the first derivative. And that's sort of mimicking that. And then you observe that because you're just putting that in near the boundary, that might be wrong. Even in the interior, it might be wrong. Where you go from one triangle because you're doing it. No, actually, for the global one, this would be only at the boundary, and therefore you need to do this corrector that corrects for the errors you make on the boundary. And once you stick those two things together at the sort of first order scale, you get a corrector that allows it to get this result. But it's homogenization, literally. There is, by the way, there's also stochastic homogenization theory, which works also when the coefficients are ergodic, stochastic ergodic. You can do similar results. So you get cell problems again, and you can calculate a corrector, and you can prove things for stochastic, for random field coefficients as well. So I hope it comes on now. Okay. So this is the result. So maybe just first some comments and then coming back to Moritz's point. So there's been many extensions. You can do non-conforming multiscale finite elements. You can do it in a mixed setting. You can do it for different PDEs. You can use these this 1D problems on the boundary to the oscillatory boundary conditions, oversampling, etc. But oversampling we'll come back to in a minute. The theory, though, relies typically on scale separation. So this is this paper, Moritz, where Ivan and Tom Howe, together with Tom Howe's PhD student, I believe it was, proved some contrast-independent theory for these special piecewise constant coefficients. And this was based on these results in that paper.
Okay. This only holds for DD, right? If you want to...
No. This is a paper for multiscale.
I see.
This is the DD paper, which is used to prove this.
Yeah.
That's what I meant, sorry. And I'm drawing this link to DD because tomorrow I will show you that there's a very strong link between these multiscale methods and domain decomposition methods, which I will draw up, and this is the first place where it popped up. Where we use these core spaces, these multiscale finite element core spaces, as core spaces in two-level Schwartz methods, proved new results that were easier to prove in the DD setting, and then you can use them to feed them back into multiscale methods and approximation theory. The really bigger extensions, so there's two big extensions, I think I have it highlighted here, there's two big extensions that make the methods stronger. Just a minute. One is to use oversampling, so you solve your cell problems not on T, but on a slightly larger region. And the other is that instead of solving local boundary value problems, you can go to solve local eigenproblems, and then you can feed more than one function per vertex to the problem, which would give you possibility to overcome scale separation issues. What was the question?
The special piecewise constant are these quasi-monotonicity?
No. This thing that I just drew.
I see. Yeah.
Things like that. Yeah. But have a look at that paper. If you Google it, he has initial CC as well, so you can remember that quite well. CC2. Okay. So that's it for the first part. How much did I just use? Did I use more than an hour?
Yeah.
Are we until
12?
Oh shit, okay. Good. So the second method I want to describe is localized orthogonal decomposition. So anyway, I have no end game, so I'm gonna just keep going, and whatever I don't do today, I'll do tomorrow, and then tomorrow we'll just have less of the material I have planned for tomorrow. Okay, so localized orthogonal decomposition is now in the direction of oversampling, but it is also, and that's what the next slide will say, it's also a representative of a different type of multiscale methods. All these methods obviously are closely related, but you can think of it as a variational multiscale method. So variational multiscale methods were developed in parallel to multiscale finite elements by, funnily enough, somebody is almost called the same. So Tom Howe is a Chinese guy who is spelled H-O-U, and this multiscale, variational multiscale method is developed by Thomas Hughes, which is an American, who is spelled H-U-G-H-E-S. But I'm going to describe you a more modern version, namely the LOD, Localized Orthogonal Decomposition method, first developed by Marquist and Peterson. So now we have a different viewpoint than I just simply element by element change my function. I want to more closely look at the decomposition of, so I picked VHMS as a subspace of V. I didn't care what V without VHMS was. So now we want to actually look at that. What's the remainder? So for that purposes, we again work on a mesh. So again, think of squares or triangles, and with a mesh with H. And then we think of the piecewise finite element, P1 finite element space, as the space VH, capital VH. So this is classical piecewise linears. And we consider a quasi-interpolation operator. So this is a slightly fancier version than L2 projection. So L2 projection, you would just sort of average over a region and then take that as the coefficient in front of the jth element. So this is sort of a scaled L2 projection, where your scaling is kind of your hat function itself. Then this quasi-interpolation operator is actually projective. It's invertible on VH, and it has nice properties, but it still only projects you into your finite element space, where we already showed the method doesn't work when we don't resolve the coefficients. So you don't get a magic projection that gives you better properties in your subspace. But what we can look at now is we can look at the orthogonal complement, so the kernel of this operator, because this is surjective, so basically the rest is in the kernel of this operator. So anything that the operator sends to 0 are functions that are not in VH, and so I can write VH as the sum of elements from V little h as the sum of elements from V capital H plus these fine scale functions. So here is what this looks like. So if you have an arbitrary U that has some small fluctuations here on the small scale, I average out over each element, and I get this interpolant, this quasi-interpolant in VH. Then the remainder has wiggles. For this particular choice of U, has wiggles all over the domain, and we call that the fine scale component. Now, the localizable, so first it's not localized, but it's localizable. So the orthogonal decomposition we're going to look at now is, so crucially, we're going to, I've put myself some notes here, so I should prepare. If I find my 7th sheet, right here. So, let me just wipe this off a bit. So, actually I was gonna, thanks for switching it off, but I actually want this on. So I just wanted to put a little side note here. So the interpolation operator from the previous slide which maps from VH to VH has these nice approximation properties, namely that if I take a UH in VH and project it, then in L2 we essentially get that the error is of order H, capital H of course, in the L2 norm, and in particular, if I take a UH in VHF, so in the fine scale, so in the kernel of this interpolation operator, then actually, or let's call this something else, VH, then VH, I can just add or subtract the interpolant because that's 0 anyway. So this is 0, and but you have still got the same interpolation result. So you get VH in H1 semi-norm, and then we're in the low contrast setting, so we can bound this from above by another constant that will depend on beta and alpha times the energy norm of VH. So what you see here is that as H goes smaller, the fine scale components, as in the picture, they really will be small. They will be of order H in comparison to the other components of the function. So we're really decomposing into fine and large scale with this operator. But the problem is, we also know that in the in the Galerkin solution, but our Galerkin solution will not converge for epsilon smaller than h. So we know that if we just stay in that space, we can't win. But what we can do is we can try and A-orthogonalize. So we can take our fine scale functions, which are fine. The fine scale functions truly are not relevant for macro scale behavior. And we can now manipulate the coarse space by making the coarse space better. So we, rather than just manipulating the functions locally on each triangle, we're actually globally manipulating them. We're globally correcting them via this fine scale projection. So what we do here is we take an arbitrary function in VH and we calculate what the projection of this arbitrary function tested against all W in VH. So this is an A-orthogonal projection into the VHF subspace. And by doing this, because we are building it with respect to the A inner product, so the bilinear form in the case where alpha is bigger than 0 is an inner product if it's symmetric. So this is a orthogonal projection with respect to the A inner product, guarantees that now this new coarse space VHMS is actually A-orthogonal. So any function in that space tested against any function in VHF gives you 0. Or again, in other language, no, I shouldn't say that. I was going to say it's aharmonic, but it's not quite because these are not the right test functions. Okay, so is it true? And yes, it is true. If you actually decompose U into UHMS and this fine scale solution now in this orthogonal complement, you actually do get almost nothing back in your fine scale. And the way we're now going to modify our basis is that we simply take so we're now again modifying our basis, but we're doing it now not locally on each element, but globally. So instead of taking the phi jh, the hat function that we had before, which is our classical nodal basis function, we are essentially projecting first, or calculating corrector by projecting into the fine scale space, and then we build the new basis function as the difference between the hat function minus our corrector. So we basically build this basis by projecting the basis functions. So here is what this function looks like. So here is the classical hat function, here is the corrector that you compute, and you see that it is actually global. So the corrector is now globally supported, and then the corrected function looks like the sum of the two, is the difference of the two. Okay, so this is great, but the problem is that you kind of have a chicken and egg story, because you have to solve a boundary value problem on the whole of omega in order to find the basis function for each basis function, when this is just overkill. So we need some extra help here, and the extra help is this result. So I'm not going to prove that today anymore. I was going to prove that today. So basically, what we can observe is that if we look at the energy, the H1 seminorm of this corrector function on omega, where we extract, where we don't take the dark region, then that energy is bounded by the energy of the full corrector function times gamma to the k, where gamma is less than 1. So if we extract more and more of the middle, we get exponentially less energy. So we've got an exponential decay of the energy in the ring, in the white ring. And that we can exploit now, because we can just say after a certain k, we just truncate. We say we don't go beyond, and we just compute our corrector in the dark gray region here, and we ignore that there is still some error out here. And we build a practical multiscale method by solving these corrector problems on the gray regions. So you fix your J, which is how many elements you go out, and you solve, or fix your K, I can't remember anymore in this notation, which is J and K. K. Yeah. So we fix our K to take maybe 4 layers or 3 layers, and we solve this projection problem, correction problem, only in this region around the vertex, and then we take our practical localized multiscale finite element space as phi jh minus this computed function. Now we're back at Galerkin, now we're back at 101 finite elements. So now we just find UH in this new space, such that the variational form is satisfied for all test functions from the same space, and the dimension of the space hasn't increased. We've just made the support of each function slightly larger, and the functions are more complicated. You had a question?
Yeah, could you maybe double explain? So I get the one before, the practical multiscale method. So what are we doing? Like, why are we doing this now?
Okay, so again, sure. So again, what I tried to say is the following. So we have an arbitrary vertex. So this is my whole omega, and I have some vertex. For each vertex, we need to build the basis. So we take first the hat function, which lives on this region. Yeah, the original hat function lives on this region, and then I calculated a corrector, and the corrector was in principle living everywhere. Yeah? And now this result, which I'm going to prove tomorrow, says that if I take slightly larger regions then the error outside, or the function outside, not the error, the corrector outside, here is super small. And this is a notion of small, because it means that the H1 norm here is less than or equal to gamma k than the H1 norm everywhere. And so what I do in the practical method is I simply solve the boundary value problem for the corrector here. And I do that for every vertex. So this is one thing I can come back tomorrow. This is of course not super cheap, and there is again links to domain decomposition to make this simpler and cheaper. But this is basically what the basic method works like. Any other questions? Mm-hmm.
Do we have some kind of expression how the gamma scales?
Yes, and I'll talk that when I do the theory. Mm-hmm. Yeah. So in fact, the nasty thing is that it depends on alpha over beta again. So it essentially, this gets close to 1 when beta over alpha is large.
The question was our parameter in that, can I get good estimates for what's a reasonable k?
Yeah. Again, we'll talk about that. Basically, you take a log of capital H layers is what you need. Okay, so this is the method now. So as with multiscale finite elements, as with classical finite elements, we just do Galerkin projection. We have the same dimension in all 3 methods. We have the same dimension of subspace, but now we don't need scale separation. So now we can really prove that this method converges with order H. So there is an extra component, which is the classical finite element solution on the fine grid. Okay, so you need to have the fine grid fine enough. Or if you, as I analyzed in the previous result, don't discretize, then this error would be gone, but then you'd have an impractical method. So this is the classical, so this goes like order little h. And this is This is the crucial thing, which now goes, there's no resonance error anymore. And then this term is the nasty bit because it has the h to the minus 1 in it. But by choosing gamma large enough, namely what you asked, order log on 1 on h, then this can be essentially made to go like h as well. And then you basically have a bound that is of order h, as if you had solved a homogeneous problem with classical finite elements. So without any assumptions on scales or regularity, and you can do the over-Nietzsche trick as well to get order h squared for L2. So here is the numerical experiment again that I showed before, and now the red line is this LOD method. And you see that for the low contrast, before even, like this is very crude, very coarse meshes. Look, this is one element per, I mean this is doing whatever, 4 elements, it's a 2 by 2 grid. Same for the high contrast, and same for the L2 norm in the high contrast setting. So the method converges as predicted O of h. And the k is chosen here as 2 times log 1 on h. Okay. But unfortunately, and I'll come back to that tomorrow, unfortunately the gamma depends, is e to the square root of alpha over beta, so when beta of alpha goes to infinity, then this goes to 1. So the theorem is still suboptimal for high contrast. But I'll stop here, and then we can pick it up tomorrow. Let me just go maybe to the last slide, and I do a partial summary. So multiscale problems are everywhere. Classical finite elements only work when coefficients are resolved. The variation is resolved, and upscaling procedures only work so far. I told you this example with the cross point, the artificial cross point. The multiscale finite element methods is a way to encode the variation directly in the ansatz space, and in the very basic multiscale finite element method, I showed you a result based on periodic homogenization. Localized orthogonal decomposition is a more modern method that also brings in flavors of variational multiscale methods to go beyond scale separation, but the absolute crucial part of it is this oversampling, that you make these regions larger over which you solve. And then tomorrow I'll talk you about the exponential decay of the LOD corrector, and I will come to the Multiscale-Spectral Generalised Finite Element Method. Any more questions? Good. Everybody happy? I did the homework. I mean, I do realize that there is not much time to do any of these, so please feel free to obviously do them at home. Please feel free to email me. You've got the video, so you should be able to see what's going on. And if there are questions, Katrin kindly agreed that we'll have sort of a joint Q&A session this evening. So you can ask me some questions then, and tomorrow as well, of course. Thanks.